Okay guys, we're going to continue with part 2 of Chemistry of Life. We're going to be talking primarily about the properties of water. And so, again, remember water is a polar molecule. So itself, H2O, those are all covalent bonds, but when water interacts with another water molecule, it acts in a polar way. And so water is really integral in all biological systems because pretty much all life requires water, whether it's inside, outside, or both around the cell. You yourself, think of your whole body as a giant water balloon. That's basically what you are. The majority of your mass is water. And so we mentioned this earlier that the hydrogen is slightly positive, the oxygen is slightly negative because of that electronegativity of the oxygen. And so it makes this positive-negative pull on the molecule, making it sticky. And so this gives water some very interesting properties that other molecules just kind of don't do very often. And so here we can see when water is actually arranged, when we can see all the molecules laid out. So we have a negative oxygen pointing to a positive hydrogen, and so on and so on. So we have this kind of up-down latticework pattern. Now this is liquid water we're looking at, and so in reality these molecules will be rolling all around and tumbling with each other in a liquid-like state. But this does give you a good representation of how these molecules would actually interact. And so we are going to be talking about these 5 properties of water. And so cohesion, again, think of those root words, co for together or with. Cohesion is when water sticks to another water molecule. So the hydrogen of one molecule of water is attracted to the oxygen of its neighboring molecule. In nature, we see this as surface tension, giving insects a surface to walk across on water where they can spread out their body mass. Adhesion is when water sticks to another substance or another surface. Whenever you measure water in a graduated cylinder, they say measure at the bottom of the meniscus. That meniscus is that curvy edge of the water, because since water is adhesive, it runs up further on the sides of the graduated cylinder. And so you measure at the bottom of the meniscus to get a more accurate reading of the actual volume of water that you're measuring. And so there's our little pond walker bug. And so we can see that his legs are they're actually making an impression on the surface of the water, but he's able to spread out his body mass enough where he can walk across the water instead of sinking into it. And capillary action of drinking through a straw, that water adheres to the side of the straw while you are sipping on it. Again, that's our meniscus line I was mentioning. So we measure by the bottom of the meniscus. And so a biological process for plants that is very important, that utilizes both of these properties, is called transpiration. And transpiration is the movement of water from the roots to the tops of the leaves, exiting the plant. And so by moving this water, so water moves from roots to the top, okay, from down up. And so this process really uses both of these mechanisms in order to work without having adhesion and cohesion, be very unlikely that water would be able to transport all the way from the roots all the way to the top tips of the tree. Alright, water is also known as the universal solvent. Again, this is basically due to it being a polar molecule. It makes a very, very good solvent. And so it's able to surround other molecules because it has positive and negative. And so here we have a chunk of sodium chloride or salt, and we have all these water molecules that are interfering now, and it's able to interfere without causing anything horrible to happen because these negative oxygens are surrounding the positive sodium and the positive hydrogens are surrounding the negative chlorine. And so a solution is made out of a solvent and a solute. So the solvent is the thing that's doing the dissolving, in our case the water. The solute is whatever is being dissolved. So like our last slide, it would have been the salt. And it's just kind of goofy, but it's fun.
But my life isn't all cherry and sweetness. Oh yeah? I put my pants on one leg at a time. Except my pants are 22 different flavors. I've got grape pants, I've got watermelon pants, and I wear them in my head. It takes work to look this good, but other than that, I'm completely normal. Well, relatively normal.
Pretty sweet.
Try any of our 22 delicious flavors.
But anyway, he was making a solution, so just kind of goofy. And so again, the water was the solvent and the Kool-Aid was the solute. And so things that are able to dissolve in water are things that are attracted to water. And so again, from our root word list, hydrophilic, hydro for water, philic for loving. And so molecules that love water are easily dissolvable in water. And so would these be a polar or a nonpolar substance? Hopefully you guessed right. Things that do not dissolve easily in water are hydrophobic. And so you might have heard of that phrase, oil and water don't mix. Well, it's not necessarily anything to do with mixing. You can force a temporary mixing of water and oil, but they will separate out over time because of hydrophobic interactions. And so again, hydrophobic, water-fearing. And so these molecules are not easily dissolvable into water, so they are nonpolar. So kind of a strange thing, ice, whenever you put ice cubes into a glass of water, those ice cubes are going to float. But most things, when they freeze or get colder, they become more dense. And so they get a little bit smaller, they condense, and so they are more dense because they have the same mass, but in a smaller volume. Ice, however, expands when it is frozen. And this is due to, again, hydrogen bonding. And so that lattice work that we saw earlier from liquid water, instead of the atoms or the molecules being able to tumble across each other and move, as ice, that bond becomes solidified. And so it makes a very crystalline lattice work that is expanded instead of contracted like many other molecules would. And so ice floating is actually a very important biological property. It allows for many things to be able to occur regardless of the temperature, surrounding temperatures. And so the surface of a lake could freeze. We know that we get ice mats on some of the surfaces around the Arctic and Antarctic. However, it doesn't freeze all the way through. And that's because the ice is going to float on the top of the water because it is less dense. And also we get a seasonal turnover of lakes where as that water, that ice melts, that cold water on top will sink and mix and kind of turn the nutrients over in the lake, making it a healthier lake. So water has a very high specific heat where it is very resistant to changing temperature. And so the way I like to describe this is if you have a kiddie pool outside full of water and you also have a parking lot, okay? Which one would you rather step on with your bare feet? Hopefully not the parking lot, because if you do, you're going to get blisters. But the kiddie pool, even though they've been out in the sunshine the same amount of time all day, the kiddie pool with the water inside of it is going to be much, much cooler than the surrounding pavement. And that's because of specific heat. It is less likely to change temperature. It will change temperature. It is just going to resist it. It's going to happen slower. At the same time, it takes more time to cool down once you do get it up to a heat. And this is what helps moderate our temperatures on Earth. And so most populations are coastal populations. The majority of the world's population lives near a coast. Water also has a high heat of vaporization. Heat of vaporization is the amount of heat that a substance must absorb to be converted to the next state of matter, so from solid, liquid, liquid to gas. And so it has a very high heat of vaporization. We use this as biological organisms for evaporative cooling. And so as that water evaporates off of our forehead when we're sweating, it's going to take a lot of heat with it. Unfortunately, here in the Houston area, there's so much humidity in the air that even when we do get hot, that the atmosphere is also already so saturated with water that it is not likely to actually evaporate from you. Also, what happens here most often that people complain about, oh, I'm so sweaty, is like, well, actually, you're not sweating, but if you're walking from the building to your car and you get all soggy in just, a couple yards, well, it's not that you're actually sweating that much, it's that your skin temperature is cooler than the outside air temperature. And so when the water molecules that are in the air hit your skin, well, they were moving fast because of the high heat temperature, but when they hit your skin, those water molecules slow down and condense on you. So it's not that you're actually sweating that much, it's that water is condensing on your skin, making you feel uncomfortable. So we're going to talk briefly about pH and buffers and things like that. And so water, H2O, can be split into H and OH. And so H plus, having more H plus in a solution makes it acidic. Having more OH minus in a solution makes it basic. Having equal amounts is a neutral solution. So water itself is neutral but when it's split and mixed in different solutions and whatnot, we can make it acidic or basic depending on whether we're putting in more H plus or OH minus. And so the pH scale is typically 1 to 14. I have seen a 1 to 16 scale, but it's not very common to see. 7 is neutral. Anything less than 7 is considered an acid. Anything greater than 7 is considered a base. And so here are some examples of different substances that and their pHs. And so pH is for power of hydrogen, and so it is on a log scale, and I might show you guys how to do a couple calculations, but I'm not going to. It's not very fun. Sodium hydroxide here, we will be working with some sodium hydroxide this year. It is a very, very, very strong base. And what bases are usually used for are cleaners. We see bleach, ammonia, oven cleaner, because they dissolve fats very easily. And so if you get sodium hydroxide on you, it'll hurt, it'll burn, and it'll be very tingly. And so you just wash it off with lots and lots of water. You should be fine. So pure water is neutral here, but then all those things that we like, sodas are acids. Most fruits are acidic. They have different acids, citric acid, malic acid, things like that, that give it that tart, sweet taste. So here we have, again, acids or anything that has hydrogen ions available to donate in the solution, and then bases anything that can reduce the amount of hydrogen-free ions in the solution. And so it usually has a greater amount of hydroxide. Buffers are anything that can help stabilize the pH of a solution. And so what a buffer can do is, if the pH is getting lower than expected, a buffer is able to donate extra hydrogen ions to the solution. If the pH is getting more acidic, then it can absorb those extra hydrogen ions. And so it can go back and forth depending on a certain range that buffer can keep stable. The environmental impact of pH is, we've seen different things. When I was a kid, the big scare was acid rain, acid precipitation. And basically, this happens whenever carbon dioxide is mixed into water. So when carbon dioxide is mixed into water, it forms carbonic acid. And so carbonic acid, itself, like if we, we'll have it in the lab, we'll make some, we'll do an experiment. But it's not particularly dangerous just to have around. But the long-term effects of carbonic acid can be very, very bad. And so with ocean acidification, what will happen is that it causes the decalcification of coral reefs and other organisms that use calcium to build shells. And so it has a big impact on these sea creatures because it reduces the amount of free calcium, the carbonate available in the water for them to utilize. On land, it affects plant life, and then plants affect everything else. We have had regions where patches of forest have died because of acid precipitation. We mostly see this, though, in areas that are not very tolerant to drought, and also they have a very small range of where they're able to utilize only a small pH range in the soil. So they're very, very picky plants. And so we kind of go back and forth on, well, if it killed those plants but not all of them, maybe the ones that survived are better, and they'll reproduce and have better plants to handle this in the future. So this was like a really, really, really big deal. You don't hear about it as much anymore, but it's still something that occurs. And so that's it for Chemistry of Life Part 2, and we will go on to carbon and macromolecules next.